Hi, in this video I'm going to talk about boosting. So in previous videos I talked a bit about these dartboards. So I had these two dartboards and I was throwing darts at them. In this I'll just imagine I throw these darts with low variance on both boards, but then the first board I'll have also low bias, and I'll have high bias in the last one. So something that'll probably look like this. So the idea of boosting is to decrease bias. So you can think of it as going from this case to this case. So this would be the goal of boosting. Great. So you can think of these as being a hypothesis, each of these points a hypothesis that's just not strong enough. It doesn't have the fitting capabilities or the complexity to actually learn the unknown target function. It doesn't have the fitting power. It might be a linear model and the underlying target function might be something that's highly non-linear. So the idea is now to combine a lot of models in a way such that they can increase their complexity together. So you'll have a lot of simple things and then you want to combine them into something that's complex. So you can think of the idea as we want to combine several weak learners. So this will be hypotheses that are almost as bad as it can get, and we want to combine these into something we'll call a strong learner. So let's just try to figure out what these terms mean. So a weak learners will be hypothesis H1, H2 to H capital T, such that for each of them, to be a weak learner will require that the in-sample error rate of this HI is at most a half minus gamma I for some gamma I that's larger than 0. So what I'm saying is essentially the error just has to be better than a half. Okay, so we're doing binary classification here. So let's just think about it. Let's say, suppose this is my data, right? And let's say that I guess wrong on the first 50% of the data set, right? You might be like, oh well, I could maybe do something worse. Let's just think about that. Is this the worst I could do? Could I do something that's worse than this? What if I maybe predicted wrong on 60% of the data? Would this be worse if I did predicted wrong on 60%? But it's binary classification, so I could just flip everything I said, and then I would only be wrong on 40% of the data. So the worst you can do in binary classification is actually a 10% wrong. I mean, you could, yeah. So in the other case, you could just flip what you're saying, and then your thing would be better. So what I'm essentially saying is, I just want something that's something very slightly better than the worst I could ever hope for. This will be a weak learner. I mean, it's allowed to be better. Then I'll try to combine these into a strong learner. And a strong learner will be some hypothesis H, such that the in-sample error rate of H is arbitrarily small. Okay, arbitrarily small. So this seems quite ambitious. It's a quite ambitious idea. I want to combine a lot of guys that's close to as bad as it could ever get. I mean, they can be better, but I'll not require it. And I want to combine these guys into something that's arbitrarily good. Okay, so I'll try to just sketch the idea here. The idea is I'll take my data set. So let's suppose I have data that looks a bit like this. I'll probably have some pluses and maybe some minuses like this, and then let's say I can only learn axis aligned lines. So what I could learn would be something like these kind of hypotheses. This is what I can learn. So I won't be able to classify this dataset perfectly with the weak learners, but I'll probably be able to do good. So the idea is I'll try to learn one of these guys. So maybe I would learn this guy. So let's say everything over here gets to be minus and everything over here gets to be plus. So then I would predict correctly on this point, this point, this point, this point, and this point. But these 2 points I'll be wrong on. So then I'll reweigh the data set now. So the points I was wrong on, I'll make these bigger. And then the other points I'll make smaller. I don't care this much about these points because I already predicted it correctly on them. We'll call this H1. Idea is now I'll try to learn again. And then maybe I'll learn this guy. So this might be H2. So now then I'm let's say everything below is minus, then this guy is correct, and 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 this guy is correct, but I'm wrong on these two guys. So then I'll reweigh the data set again, and maybe these will be a bit smaller now. This guy will increase a little bit, and this guy will increase a little bit, and then these will be very small now. I don't care about them that much anymore. And then I'll combine these lines in such a way that in the end they'll probably give me something that'll classify the data set correctly. Maybe I'll get something like this, so this is the idea. So I'll take some weak guys and I'll combine them by reweighing the data. So there's two questions we need to solve here. The first one is how to combine all the hypotheses, and the second question is how to weigh well, okay, maybe there's actually three kind of questions. How do we weigh the hypothesis? So let's say how to weigh the data, right? Yeah. So in each iteration we have to weigh the data, and then we also have to combine these hypotheses in a way. So there is a way, an algorithm called AdaBoost. It's an adaptive algorithm, so Ada for adaptive. And by doing this, we will be able to get that the final hypothesis, the one that combines all of them, H, let's call this H, the in-sample error rate of H will be at most e to the minus 2 sum of is1 capital T. So let's say we combine T hypothesis, and then it'll be the sum of these gamma I squareds. So let's just suppose that all of these gamma i's is, let's say each of the lines gets in-sample error say a quarter, then this is a quarter. Let's maybe just make it, let's say each of the hypotheses I learn are better than a quarter, then each of the gamma i's will also be less equal a quarter. So then this thing will be less than equal to e to the minus 2 t times a quarter squared. So this is like an 18th, right? So this will be like it'll be exponentially decreasing in t. This is the thing I wanted to show you, right? So you can maybe try to do another example, and maybe I fumbled around with the small numbers, but the idea is that the in-sample error will be exponentially decreasing in t. So now you might be a bit scared with thinking about overfitting, and we'll talk about this later. It actually turns out that this thing typically doesn't hurt generalization. It will overfit, but it won't hurt generalization. But so this is the bound you get, and it's probably better than anything you would ever hope for. I mean, I was very surprised when I saw these bounds. So I'll briefly try to look at the algorithm and try to give you an idea of how it works, and then maybe in later videos I'll talk a bit about the overfitting problem, or why this is not a problem, how people have tried to explain it, and also I'll maybe talk a bit about how can we prove this. If not, I'll give you a link. I'll definitely give you a link to the proof. That's this very nice proof here. So this is the bound you get, and that's a proof here. It's rather brief. It's a very nice proof. So let's look at the algorithm. So this is the AdaBoost algorithm. So I just took it from this guy who published the algorithm. This is one of the authors. He also made a note where he explains it very nicely. So this is where I just took it from, and this is similar to the original article. Great. So the input to the algorithm is like usual in our machine learning setting. We have data points x1, y1, and in this case we just denote the number of points by little m instead of capital N. Then there's this thing called, we have this distribution over all the points. So we'll have, or maybe I should just mention, we have binary classification as usual, but then we'll also have this distribution on all the points. So this will be, for each of the points, we'll have like a way, think of it maybe as a probability of seeing the points, or maybe let's call it a weight on the point. Actually, this is probably better. We'll have a weight for each point, weight 1, and we'll have this for all the points, weight M, and then we'll require that each of these, the sum of these weights is 0, right? So all of them has to be positive, and they have to sum to 0. So this is a distribution. So we'll actually denote it D instead. So this is what we write here. So the initial distribution on the points is uniform. Each point will have the same weight. So this is the initial requirement of the initial step of the algorithm. Then we'll have capital T steps, and the idea is for each of these steps we'll learn a hypothesis h little t. So we'll learn hypothesis 1, hypothesis 2, and then have hypothesis capital T. And then what we want in the end is to combine all of these hypotheses into a final hypothesis. And the way we'll do this is we'll have a linear combination of each of the, we'll sum each of the hypotheses, and then we'll have some weight for each of the hypotheses. Okay, so now the idea is these steps could somehow be condensed into learning the ith or the tth hypothesis. So we train a weak learner using the distribution we have on our dataset. So this kind of corresponded to how I drew the sizes of the point. How important are the points now? This is what the distribution basically says. So initially they'll all be equally important, and then we'll just learn normally. But in other iterations, we might have that one of the points is maybe the only one that's important, and we don't care about anyone else. Then we'll trigger a hypothesis using this, and we could use any algorithm to do this. We could use the perceptron, we could use linear regression, we could use logistic regression, we could use maybe support vector machines, neural networks. In practice, it works pretty good if you use these decision trees. So typically one uses decision trees. We get a hypothesis, and we want to have a hypothesis that has a low weighted error, and this is the low weighted error. So you can think of it kind of as an ensemble error rate, where we have like so you can think of it kind of as this, I guess. So where we just have we just incorporate the weight of the points. So this would be they write it as dt of I. So this will be the weight of the ith point in the tth iteration, right? So like this would normally we just wouldn't have this part, and then this could be your ensemble error rate. So now we'll just weigh each of the points by this distribution. Great. So now we got a hypothesis. So we already decided that we wanted to combine them as a sum where each of had a weight, and then it turns out, and I mean to realize why this is the case, why you have to weigh it like this, you need to look at the proof. It just makes the proof work. This is I think the guys who made this algorithm was actually trying to make the proof work, and then they came up with this, and then everything just worked. I think this is how it came into existence. I don't have any other intuition why this is what you need to choose, but this will be the weight of the hypothesis. So in this step you'll learn a hypothesis ht, and now you'll learn the weight that has to go before this hypothesis in the final sum. Then in this final step we reweigh the training data, the dataset, or the distribution on the dataset. So okay, the distribution, they are both called capital D. So let's just we reweigh the dataset. So for each point you compute a new importance for the point. So let's just think about what this says, and for now we'll just not care about the set t thing. Let's just not care about this for now. Let's just think, what does this say? Well, it just says we take the old weight we had on the point, and then we multiply by this e to the minus alpha t y I h t on xi. So let's just think about what this is. this is the interesting part, I guess. So there are 4 cases here, right? Each of these will be -1 plus 1. So we could have y1, so we can maybe write it as this actually, and let's just see ht of xi. So it could be -1 plus 1, -1 plus 1, with -1, -1 plus 1 plus 1, okay? So in these 2 cases, then our algorithm predicts it correctly, and these cases it predicts wrongly. So the thing you need to realize is if they agree, then we get +1, right? So then, and if they disagree, we'll get something negative, right? So when I multiply these things together. So then what this thing says is the importance of the point. Well, if I predict correctly, right, over here, then the importance of the point will be something, well, this guy will be positive, right? So then it'll be something positive times something positive, and then a negative sign. So then it'll be small, right? So it'll be e to the minus something. So it'll be small if I predict correctly. And then if I predict wrongly, right? So if this is a minus, then this minus from this guy will cancel this minus and it'll be a plus. And then it'll be large. So if I predict correctly, then this thing will be small. And if I predict wrong, then this guy will be large. So this is basically what we saw over here. Well, the points that I did mistakes on, I'll weigh them large, and the other guys over here, I'll weigh smaller. So this is essentially what this step says. So what this step does. Okay. So this is essentially it. There's just one step left. So we'll get some value for each point. So maybe we'll have x1, y1, x2, y2, all the way through xm, ym, and then I'll have a weight on each of these, right? d1, distribution 2, all the way to distribution m. But I computed this in this weird way, so now it's not clear that the sum of all these dt plus 1 i's is 1, right? This is not clear. So what I'll do is I'll divide each entry by the sum. So I'll normalize it so it sums to 1. So I'll take I'll take all of them and then divide it by the sum. So this is basically what the thing in this CT thing I divide by. It's just a normalization factor, so they all sum to 1. So this is the idea of the algorithm. So now I try to try to explain what the different steps kind of corresponds to. So this is it's a rather simple idea, but then there's a lot of details you have to make work for the algorithm. So yes, and I also said this thing. So this is what you get for this algorithm. It's a very strong thing. Like you'll get exponentially smaller ensemble error in T. So you'll definitely be able to get 0 ensemble error if this is what you want. So I'll just briefly mention the overfitting, right? So I mean, if the ensemble error rate will decrease exponentially, it'll probably hit 0 pretty fast, right? So this will maybe be the ensemble error rate. So typically what you expect the outer sample error rate to do is something like this. So if it's not clear to you why you would expect this, you should maybe read a bit more about learning theory. If essentially what happens is we're focusing too much on the data set we're looking at right now, and then we're fitting the noise, and then what we learn won't generalize to data points outside of our data set. So when we get new data points, we'll perform more terrible because we just learn too much. What happens in boosting is actually something very different. This is typically what you see. So even after the ensemble error rate is 0, if you keep on learning, you will generalize better and better. So explaining this is still an ongoing research area, and I won't have time to tell you why this any things about this, but this is a very nice property to have, and yeah, this is one of the properties boosting have. So I think this is what I had to say. This video wasn't that concise. I want to apologize about this, but I didn't have this much time to prepare it. So this was kind of like unprepared talk about boosting. If there's any questions or anything you want clarified, please point it out, and maybe I'll make a more structured video in the future.